Hello everyone. This is a continuation to the previous lecture, and in this lecture I would want to continue with the problem that we had started. The problem is in front of you. I think we discussed till 4 parts, till part D, but I will re-explain from part D, and we'll do part D, E, CD. Okay, I think I numbered it wrong, but yeah, I will explain these 4 parts to you and this part. Just for a recap, the problem we were trying to solve is that we had a standard deck of playing cards which has 52 cards, and 5 card poker hand is to be chosen. 5 cards unordered without replacement, and all hands are equally likely. We have found the probability of all hearts exactly 1 ace and 2 aces, and we have also seen what are the total different number of 5 card hands that are possible. Now we will do exactly 1 pair, 2 pair, and 3 of a kind. So by here, what does by here pair in this thing? Pair means two of same number. Okay. So either I have 2 aces, or I have 2 twos, or I have 2 jacks. And this can be any two of the 4 types. Okay. Any two. So again, consider each task as a group of tasks, and if you know the number of ways in which each of these subtasks can be done, and then by the fundamental theorem of counting, you just multiply them. And yeah, just to remind you, the denominator is still same, which is 52C5. That is, we are choosing 55 cards from 52 cards. So the total number of outcomes without any restrictions, without any certain favorable things that you want. This is just the plain truth that this is all the different type of cards that can come, given that order doesn't matter and without replacement. So one card can come once. It's not that you're taking one card, putting it back, and you can get it again. Okay. Now, let us look at this. So we want exactly 1 pair, right? That's the question. So exactly 1 pair of aces, or 1 pair of jacks, or 1 pair of queens, like that. And by exactly 1 pair, I mean it's not at least 1 pair or at most 1 pair or something like that. It is exactly 1 pair. So I should get a pair of two numbers, and apart from that, the other 3 numbers, since we are picking up 5, right? So the other 3 numbers should be different. So there should be no pair in the other 3 because we want exactly 1 pair. Okay, so first let's deal with the subtask of getting 1 pair. Okay, now we have 13 different numbers. Okay, we have seen this. So first of all, I will choose one number out of it, right? And that can be chosen in 13C1 ways. And once I get the number, suppose I get 10. Now this 10, there are 4 tens, right? One of each type, and I can take any two from these 4. So that is also a choice, and there are 4 C2 out possibilities from there. Okay, now we have finalized our 2 numbers, right? Now we have 3 numbers left. So first of all, the 3 numbers should be different from each other, and it should be different from this number as well. So out of the 13, one number is gone here. I don't know what that is, but it is some number. So I am left with 12 options, and out of that I will choose 3. Okay, now suppose these 3 are jack, queen, king. Suppose it can also be a number 10, queen, king. Okay, and we have 4 of each we have 4 of each of these cards. So for each card, we have 4 types, right? So all of these 3 that I get can be any of the 4. So once I choose 3 numbers, the total number of ways these can be chosen is 4 into 4 into 4. Again, this is also by fundamental theorem of counting. I know that 10 can be chosen in 4 ways, queen can be chosen in 4 ways, king can be chosen in 4 ways. So what combinations of 10 king and queen can be chosen? It's 4 into 4 into 4. So that's it. This is our event. This is our event of interest, and this is the total number of ways that event can occur. So this is our numerator, and denominator is this. Okay. Now, the second question related to pair was that you get 2 pairs. Exactly 2 pairs. So what this means is that I first have to select one pair. I first have to select what are the 2 different. I have to first select 2 numbers, okay, from the 13. Suppose I get a jack and I get a 2, okay. These are the 2 numbers that I will get. I get, suppose, and then there are 4 C2 options of both that I can choose, because I have 4 jacks and I have 4 twos, and I have to select 2 of both. So there can be 4 C2 ways in which I can choose 2 different types of jacks and twos. So that counts for that. All right. And then the other pair, the other last number that is left, since we're choosing 5 numbers, has to be from those 11 numbers which are left. It can't be any of these numbers which we have chosen. And so that is 11C1. And again, that can be chosen in 4 ways. So that is into 4. And 52C5 is our denominator again. Okay. Yeah, so that's the probability of exactly 2 pairs. Next, we have 3 of a kind. So this is again, I choose one number. It can be 4C3. So whatever number I choose, I have to choose from the 4, and there are three options I have to choose. So there are 4C3 ways in which I can choose it. And then from the leftover numbers, I will choose the 2 numbers that I have, that I need, and those can be chosen in 4 square ways. And the denominator is, now full house means 3 of one kind, 2 of another. So this is very easy given that we have solved the above 2 things. So this is a homework. Okay. And there's one question which I have added, which is like a side note which you should know. That's why I have included it. Now, how many different 5-card poker hands are possible if the order mattered? So if the order mattered, now till now we have been dealing with order does not matter. So this will be an ordered without replacement case. And this also we have seen this. For this we have this common notation np3, which is n factorial by n minus r factorial. So 52p5 would be our denominator in that case, because now the order also matters. So this would actually be more than 52c5, because say I have 5 numbers that I've chosen. Those 5 numbers can be ordered in 5 factorial ways, and all those 5 factorial ways will be part of this, which was earlier not part of this. So yeah, So yeah, that's what I wanted to cover. I was not able to cover this full exercise in the previous lecture, and I think now I have done justice to the question. Let me know if you have any questions, and I'll meet you in the next session. Thank you.